This topic is evaluating limits to find the vertical and horizontal asymptotes of a function. So in particular, we're going to be looking at rational functions here. In college algebra, we learned how to find horizontal and vertical asymptotes by looking at the end behavior of the function, which gave us top-heavy, bottom-heavy, and balanced. And we were able to find the vertical asymptotes of the function by factoring and simplifying the rational function and then looking where the denominator equals 0. So there is an approach that we already know. We should already be able to find vertical and horizontal asymptotes of rational functions using those techniques from college algebra. But we actually want to use the techniques of calculus to find the vertical and horizontal asymptotes. So remember, when we're saying horizontal asymptotes, we're wondering if it approaches a number like y equals 2, where you would see the function do something like this. But all we care about is the end behavior for horizontal asymptotes. That end behavior is as x goes to infinity and negative infinity. So these two right here are going to indicate whether we have any horizontal asymptotes. The next one was vertical asymptotes, and vertical asymptotes only could potentially occur where the denominator is equal to 0. So if we look here, x plus 1 is our denominator. Notice if I plug in x equals negative 1, that would be where we would potentially have a vertical asymptote. We'd still have to check. It could be just a whole, not a vertical asymptote. So that's why we want to look at the behavior around x equals negative 1. Notice that is the last one right here. So this one right here will be indicating whether we have a vertical asymptote. The last one that they threw in here is as x approaches negative 3/5 to the right-hand side. I can tell you right now that's going to make the numerator equal to 0, but not the denominator. This is just to throw students off to see, do you really know where the vertical asymptotes occur? Because a lot of students mess up and think that the numerator dictates vertical asymptotes, and that's not true. What dictates your vertical asymptotes is your denominator. So let's read the problem here, and we're going to attack this one at a time. It says, let the function f be defined as follows. Answer the following. F of x equals, it's a rational function. In the numerator, we have 3 plus 5x, and in the denominator, we have x plus 1. Find the following limits and use the exact values in your answers, not decimal approximations. The first one is the limit as x approaches infinity of f of x. We can do this pretty much the same time as the limit as x approaches negative infinity of f of x. These are our infinite limits. Hopefully you've already covered the topics about infinite limits with rational functions, and you remember the trick. The trick to find infinite limits is to take that original function, f of x, which equals 3 plus 5x over x plus 1, and the idea is you want to look at the highest power of x in the denominator. Here it's just x, and so the trick was that we were going to divide every single term by x, which is the same thing as multiplying every term by 1 over x. So when we do that, we would distribute that 1 over x through to each term. So my first term would be 3 times 1 over x, which is 3 over x. The next one would be 5x times 1 over x, which is 5x over x. In the denominator, we'd have x times 1 over x, which would be x over x. And the last term would be 1 times 1 over x, which is 1 over x. We go and try to simplify each one of those terms. 3 over x does not simplify. 5x over x, the x's simplify. We would be left with just a 5. In the bottom left, x over x simplifies. We'd be left with just a 1, and then we have 1 over x. So this function is the exact same thing as 3 over x plus 5 all over 1 plus 1 over x. So instead of finding the limit as x goes to infinity of this original function, we're going to find x goes to infinity of this modified version of it, which is perfectly fine because we do have equal signs between every single step. So again, when I look at the limit as x approaches infinity of f of x, that has to be the exact same thing as the limit as x approaches infinity of that 3 over x plus 5 all over 1 plus 1 over x. Why do we care about that? Well, now we're just going to take the limit as x goes to infinity of each one of those parts individually. So if I take the limit as x goes to infinity of the first part, remember I have a constant up top and I have an x in the denominator. Anytime you have a constant over x, we notice that that function has to approach 0. When I look at the limit as x approaches infinity of the top right, which is just 5, the limit of a constant is a constant, so that's going to approach the value 5. The limit as x goes to infinity of 1, again, that's a limit of a constant, so it approaches that constant. That'll just go to 1. And then I have the limit as x goes to infinity of 1 over x. Again, you have a constant on top and x in the denominator, so that has to go to 0. So when I do that, what do I get? In the numerator, I had 0 for my first term, 5 is my second term. In the denominator, I had 1 for my first term, 0 for my second term. So it looks like I have a 5 over 1, which is just 5. So what's the limit as x goes to infinity? It is 5. Okay. We're going to make the exact same argument for the limit as x goes to negative infinity. The limit as x goes to negative infinity of this function is going to be the exact same thing as the limit as x goes to negative infinity of 3 over x plus 5 all over 1 plus 1 over x, the exact same function, and absolutely nothing is different. It doesn't matter if you're doing the limit as x goes to infinity or negative infinity, as long as you have a constant over x, both of those terms go to 0, and the limit of a constant is always the constant, regardless of which x value you're going to. So this is literally the exact same thing. In the numerator, 0 plus 5, in the denominator, 1 plus 0, which is 5 over 1, which is 5. So I know the limit as x approaches negative infinity is also 5. Okay, what does that give me? That gives me the end behavior of my function. To the right, I approach 5. To the left, I approach y equals 5. That means with this function, I have a horizontal asymptote, and that horizontal asymptote is y equals 5. Again, where do I find that horizontal asymptote from? And I'm going to do some highlighting just to let you know. Just to kind of point it out, if I go to infinity and negative infinity, that's what's giving me my horizontal asymptote right there. Let's look at this next one. It wants to know the limit as x approaches negative 3/5 from the right-hand side of my function f of x. I'm going to try this one by direct substitution first. Let's see what happens. When I do this, I get 3 plus 5 times negative 3/5 all over negative 3/5 plus 1. I'm going to go ahead and plug that into my calculator just to be safe. So I'm going to do 3 plus 5 times negative 3/5. Oop, get that 5 in there. Close that out. Go into the denominator, and then I'm going to do negative 3/5. And then I have that plus 1. Going to go ahead and hit enter. When you do this, you're going to get 0 on top and a different number on bottom, and 0 divided by a number is 0. So this one actually worked by direct substitution. We just get a value of 0. So plugging in negative 3/5 gave us 0 in the numerator. So that's the limit. And of course, if that's the limit at that point, then that's certainly the right-hand side limit as well. Okay. So what would happen now if I plugged in a negative 1? Notice if I plugged in a negative 1 to my original function, I would have 3 plus 5 times negative 1, which would be a negative 2. And in the bottom, I'd have negative 1 plus 1, which would be a 0. So here we're getting a number over 0. If you remember, anytime you get a number over 0, that's where you have a vertical asymptote. There is no factoring and simplifying we can do here. There's nothing in common. So the only way to prove this last one is to actually do a table of values. Nice thing is, they're only asking us to do a table of values from the left-hand side. So we're going to look at x values to the left. We need 3 numbers to the left of our desired value, which is negative 1. And we're going to plug that directly into our function. We'll plug it into the original function, which was 3 plus 5x divided by x plus 1. Again, how do you find numbers to the left? You take that x value and you subtract 0.1. When you subtract 0.1, you would have negative 1.1. Then you're just going to get closer and closer to it. So that would be negative 1. Oh, sorry, I did that wrong. If I subtracted 0.1, yeah, I'd have negative 1.1. Then I'd have negative 1.01, and then I'd have negative 1.001. Be careful to the left now, because we're negative numbers. We're not doing the nines. That's what was looking off to me, as usually it was like the 0.9, 0.999, 0.999. So you just got to be careful on this one. When you go from the negative sides, you actually need to plug in the negative 0.1, and then you just get closer and closer to it. Okay? So again, I'm numbers below negative 1, but getting closer to negative 1. I'm going to fill in this table using my table feature on my calculator. I hit table, I clear out whatever's in there. I have a fraction. In the numerator, I have 3 plus 5x. Ooh, let me clear that out. A fraction. On top, I have 3 plus 5x. In the denominator, I have x plus 1. Okay. I hit enter. Doesn't matter where I start or step. I need ask x on there. I'm going to hit OK. If you have numbers in there, just go ahead and delete them out. Clean that table up. Start plugging in your numbers. Negative 1.1 is below. It's to the left of negative 1. Then I have negative 1.1. And then I have negative 1. Negative 1. Give me a second. 1.01. And then I have negative 1.001. Enter. And there we are. So there's our values. We have a value of 25. We have a value of 205, and then we have a value of 2005. So notice, as I go from left to right, as I get closer and closer, and here we know that the function does not exist at that point. As I get closer from the left-hand side, I have 25, 205, 2005. My numbers are getting bigger and bigger, and they are approaching positive infinity. So that value right there would be infinity. Anytime you're plugging in a single number and you get infinity or negative infinity, that is going to represent a vertical asymptote. So if you have an answer here that's infinity or negative infinity, and you're plugging in a single x value, we're plugging in the x value of negative 1, then that is a vertical asymptote. Vertical asymptotes are vertical lines, and vertical lines are always x equals some number. So what is the x value here? It is x equals to negative 1. So our vertical asymptote would be x equals negative 1. Okay. Again, we could have gotten this answer using algebraic techniques that we have already learned for rational functions. We've already learned horizontal asymptotes, top heavy, bottom heavy, unbalanced. We already learned vertical asymptotes, factor, simplify, then set the denominator equal to 0. This is more of a calculus version of finding them, and the reason that this actually is better is because the formal definitions of vertical and horizontal asymptotes require that you do infinite limits or limits at infinity. So vertical asymptotes are example of infinite limits. Horizontal asymptotes are examples of limits at infinity. I hope that helps.